Welcome back to the Datarekha audio guide. I'm Diya.
And I'm Arjun. Here's a number that sounds impossible. A single LLM server on one thread juggling 10,000 requests at once. Today, why that's not a trick. It's the right way to build.
Okay, set up the problem. My endpoint works in testing. A client wants 10,000 concurrent requests. What's my instinct and why is it wrong?
Your instinct is either spin up 10,000 threads or buy a 100-core server. Both are wrong. And here's the analogy that makes it obvious. Imagine a restaurant where one waiter serves one table for the entire meal, takes the order, then just stands there staring at the kitchen until the food's ready. That waiter is blocked. They're doing nothing for most of the meal. A 50-table restaurant needs 50 waiters.
Versus a waiter who actually works the floor.
Right. The competent one takes table 1's order, fires it to the kitchen, walks to table 2, checks on table 3, comes back when table 1's food lands. One waiter runs 20 tables because the slow part, the kitchen, frees them up to do other work. And the LLM is the kitchen. Generating tokens takes hundreds of milliseconds to several seconds. Your server is the waiter. Sync is one waiter per table. A sync is one sharp waiter working the whole floor.
So why is waiting on an LLM specifically the case where this matters? What's special about it?
Because the work is what we call I/O bound. Walk the timeline. Sending the request takes microseconds. Receiving the bytes back takes milliseconds. But the middle, waiting while the model generates, is basically the entire request, and during that wait, your server does nothing. No computation, no CPU. Just waiting on bytes from a remote host.
And that's different from, say, running a model on my own machine.
Completely. That's CPU bound. Every millisecond of elapsed time is a millisecond of actual computation. The core never idles. And that distinction is the whole game. Because async only helps when there's idle waiting to fill.
Let me make the sync failure concrete. Why exactly does the thread per request server fall over at 10,000?
Each OS thread needs a stack. Call it 1 to 8 megabytes. 10,000 threads is somewhere between 10 and 80 gigabytes of memory before you've written a single line of your own logic. And on top of that, the OS is context switching between all of them thousands of times a second, burning CPU to manage threads that are, again, just waiting. In practice, these servers cap at a few dozen to a few hundred workers, then they reject or they
So how does the async version dodge all of that? What's actually holding the state of all those waiting requests?
One thread runs an event loop, a scheduler that keeps asking who's ready to run. Each request is a coroutine, a function that can pause itself at a marked point called an await. When a request hits await the LLM call, it yields control back to the loop. The loop grabs another coroutine that has data ready, runs it to its next await, and so on. When the first request's bytes finally arrive, the loop resumes it right where it parked.
And the magic is that a parked coroutine is cheap.
Almost free. It's a few kilobytes of state on the heap, a saved frame and a note about where to resume. 10,000 of those is tens of megabytes, not gigabytes. No thread stacks, no context switch thrash, no kernel scheduler grinding away. The ceiling moves from how many threads can the kernel manage to how many connections will my provider allow, which is a far friendlier limit.
Now, I want to be careful with vocabulary. People say concurrency and parallelism like they're the same thing. They're not, are they?
They're really not. And the kitchen makes it crisp. Concurrency is one waiter interleaving 20 tables. Progress on many tasks, but only one actively running at any instant. Parallelism is 4 cooks each making a dish at the literally same time on different cores. For LLM, work the network wait is the bottleneck, not the CPU. So concurrency on a single core is perfectly enough.
Which means, and here's the trap, I bet. If I take some heavy CPU work and just wrap it in an async function, I get nothing.
Worse than nothing. This is the single most common async mistake. If a function doesn't actually await anything, Putting it in an async definite doesn't make it yield. It runs straight through and blocks the entire loop for its whole duration. So one 500 millisecond local embedding computation freezes every other request on that loop until it finishes. Async doesn't speed up CPU work. It just gives it a dangerous disguise.
So the real fix for CPU-bound work is a separate process, not async.
A process pool or a thread pool if the work releases the lock, or a dedicated GPU service. Different tool entirely.
Alright, even on the I/O side, 10,000 cheap coroutines all hammering the provider at once still sounds like it ends badly.
And that's the last piece. Back pressure. You put a semaphore in front, which is just a counter that lets at most say 200 coroutines through at a time. Past that, requests queue cheaply inside Python, not as OS threads, and drain in order as capacity frees up. Without it, a traffic spike piles up thousands of awaits. You blow through file descriptors, hit the provider's rate limit, and cascade into 429s and kills. The semaphore is what separates a prototype from a production service.
There's one detail I'd hate to get wrong. The shared client.
Crucial. You create one async HTTP client for the whole process and reuse it. It pools the connections. If you construct a fresh client inside every request handler, you open a brand new TCP connection every single call. And at scale, that's slower than the sync server you were trying to escape. One client, shared, for the lifetime of the process.
So the one sentence to walk away with.
Async wins when you're waiting, not when you're computing. For LLM calls, you're almost always waiting. So one event loop, one shared client, and a semaphore to hold the line.
The fast server is the one that knows how to do nothing gracefully. That's the Datarekha audio guide. Catch you in the next one.